لا لا مش عندنا عشان نشتغل اي تي بس هو ده اول مشكله دلوقتي شايلها طبعا اي تي الحرب اللي
بس ولا تتكلم في المايك اللي معاك؟ لا لا.
Good evening. Now let's welcome Yusra Farhani. Yusra is a researcher in quantum error correction at the Niels Bohr Institute of Physics. Also, she is an engineer researcher in quantum algorithms at the Institute of Applied Science in Celine in France. Also, she is a research assistant at Qatar Communicating Research Institute, founder of Quantum Africa, and the winner of the Arab Young Pioneers Award in Quantum Computing by HIS Excellency of Sheikh Ziad bin Mohammed bin Zayed Al Nahyan.
Assalamu alaikum. I just don't want to start as long as there is not enough people here. So can we just ask for the rest of the people to join if that's possible? Okay. Yeah, I don't want them to miss. That's the thing. Okay, cool. Okay, cool. So first of all, I'm really thankful for the hackathon organizers, Dr. Yusuf and Dr. Taha, for the invitation. Actually, it's been like a hectic 5 months, like the past 5 months. I've been like going around different countries, attending this type of like hackathons as a speaker, as mentor, as judge, like going from Rwanda to Senegal to Ghana to Thailand. And now I'm here in Egypt, and I'm so happy that it's happening in Arabic countries, it's happening also in Africa in that extensive way. So this is really promising. So I've been like thinking what type of topics I would go and talk about it in this small or few minutes. And then I said I will go with quantum machine learning as it's like my field of research, although I do quantum error correction. And then this presentation is going to be a sort of debate because I'm a little bit optimistic. At the same time, I'm pessimistic. So your presentation this morning relates a lot to my presentation now. So the title of my presentation is Quantum Machine Learning, where we are right now, what is the actual state of the art, and what is next, what will happen, and how we should approach quantum machine learning in the next few years or few months, let's say. So I'll start with a question. What is behind AI? If we think of artificial intelligence, what are the main pillars or core of AI? I'll take some answers. Like there are 2 answers or 2 possible answers. The first thing is, now I mean like if we don't have these 2 things, we won't have AI in the first place. Math and computers. Okay, so computers is a part and the other part is data. So if we don't have computational power and data, we won't be having any AI, any Gen AI models like GPT and Gemini, etc. So the most interesting part for us today is the computational power, is the fact that we are here all thinking of a new way of computing, which is quantum computing. So we think of the power of the actual hardware and the rapid evolution, especially like between 2023 and 2025, where a lot of companies are competing so hard to get the most powerful machine with less noise and more applicability, I'd say, in different fields. So we have IBM Quantum, we have Google, we have Microsoft, we have D-Wave, AWS, and many, many other hardware providers trying to do their best to come up with that robust, I'd say, architecture that will allow us to run all the algorithms that we are working on. So the thing is, the algorithms are far away and very, very far from the hardware. We did a lot of work since years now. For example, for the case of quantum machine learning, it started first in late 2016. And then the first work that has been published, I guess it was in 2018. So it's a little bit earlier before the hardware. So we tried to come up with several types of algorithms. For now, there is more than 6,000 published paper on arXiv between only like 2024 and 2025 in quantum machine learning. And then publications are really like going into big conferences and proceedings like NeurIPS, ICLR, and QIP, and quantum information. And then there are specific labs and specific companies that are doing quantum machine learning. So in that case, we are asking the question, are we doing quantum machine learning in the right way? This is like a social dilemma, I would say. A lot of debate going in this area. And the question that we ask often, should we invest in quantum machine learning if classical machine learning can simulate every or many claims? If we think of reinforcement learning, for example, I would never see the potential of having quantum computing in reinforcement learning. That's one of like the arguments that I always use when we try to debate about the advantage of QML. But this doesn't deny the fact that we do have some really good applications of quantum machine learning, but these applications are really inspired from the quantum phenomena and not just inspired from the classical way and how we do classical machine learning in the regular way. So there is different like definitions of quantum machine learning in the literature. The first one is like the study of algorithms that run on quantum computer and that are designed to learn patterns from data. And the second one is like a discipline that gathers quantum computing, math, and statistics all together to create that new emergent field of QML. But the thing is with the hype, like AI is making a lot of noise lately, and then comes quantum computers, and then people went over the hype to combine them both. So a lot of people are talking about quantum computing plus AI, what will happen. I saw like latest announcement from Quantinum, is like one of the famous like companies that are doing quantum machine learning, that they are working on a whole project called GenQ AI. So it's like generative quantum AI. And I don't know how the quantum NLMs will work and how they will work like in terms of the actual hardware that we have. So it's been a hype. So now people are shifting from thinking of the fundamental algorithms behind quantum computing to applications of QML in different fields, which is something that I mostly disagree with. But yeah, we'll see some optimistic applications of quantum machine learning as well. So the first thing that made researchers think about why we should use quantum machine learning is when we think about like quantum computing in its core, we do have some interesting phenomena that comes from quantum mechanics and quantum physics, such as superposition and entanglement. The fact that we can explore multiple solutions at the same time. We can entangle qubits in a way where we make sure that there is a strong correlation between data points. So there are like several classical machine learning challenges that we pointed out in that field and that we tried to see what is the alternative, how can we solve them in the realm of quantum computing. The first one was the large feature spaces that we have in our like classical machine learning models. The second problem is the high dimensional data. But when we talk about high dimensional data, we need quantum memory. So we referred this morning, like this is a real issue if we want to get or process high-dimensional data using quantum computers at the moment. And then we have the slow kernel methods, the non-convex optimization when it comes to loss function, etc., etc. So that are potentially like a potential advantage. I'm not saying the quantum advantage, because there is a potential to have some advantage when we try to solve these type of problems using quantum computing. A lot of propositions like VQEs, QAUA, quantum kernel methods, which are somehow good methods to calculate or to compute the kernel faster and in more secure way, where, for example, you're just like exchanging data points in a very secure way, where you don't really have to care about data security in terms of like sending the data from a kernel to another. So these are like potential advantages for QML. I came across this paper. It's been written in 14 March 2024, and it's quite interesting. The title is like GPT on a quantum computer. I don't know if any of you here have read this paper. No? Okay, so this paper came up from the university, same data when I do the measurement because of the noise. So this is optimistic when you think of it from an approach of, yes, we're just using less qubits in order to encode this amount of data set, but then we will have the noise. We have more problems in the current hardware that will not allow us to have this like immense computational power. So I think of like quantum machine learning as we need to look to quantum machine learning from the perspective of what are the problems, the real problems that quantum computing can be used to solve in classical machine learning. So classical machine learning has been doing really well when it comes to like accuracy, really good predictions for certain problems, many other great applications. But the question here is not how can we create a version of machine learning using quantum computing. It's more of how can we ask the right questions, how can we spot the right problems where we can use quantum computing efficiently to solve these issues. And the thing I'm doing lately is like I'm really exposing quantum computing to the ML community, like the classical machine learning community, people who have never experienced quantum physics and quantum mechanics. I try to explore like other problems that I might not see when I'm really involved in the quantum computing field, in quantum physics and quantum mechanics, but themselves, they can see them in classical machine learning. And then this discussion would create an open ways or more ways to navigate this field and come up with new algorithms that might be useful. And then we can talk about quantum machine learning in a way of maybe having the advantage from quantum machine learning. So it's more of like which problem we are solving and not like, let's just create a quantum version of the CNN or the, I don't know, SVM or any type of other classical algorithms. So there are several use cases. One of the algorithms that I've been discussing with some people here in the conference is the quantum Hadamard edge detection. I don't know how many of you have heard of this algorithm before. So it's a recent algorithm that has been created in late 2023 and then has been developed more in 2024. So, you know, like the regular algorithm, the classical algorithm of edge detection. So edge detection is a mechanism that we use for image processing so that we can like extract or like highlight the edges of the picture. It's been used so much in like medical imaging. This algorithm, like the people who came up with this quantum Hadamard edge detection, they were really smart because they thought of the whole way of doing edge detection in a quantum way. So the exciting thing about this algorithm is not the accuracy and not the precision, but the complexity of the algorithm itself. So when we compute the gradients, we basically need a lot of features. So the features, the more the data set gets bigger, the more features we need inside, like to do the calculation of the gradient. As Dr. Allen mentioned, it's almost like NP hard problem. So this algorithm can compute the gradient in O1 complexity. So it's completely independent of the number of features. And this is because of the superposition. So they are using the Hadamard gate in the architecture of this algorithm to be able to do that. This is fascinating. This is one of the good applications that captured my attention in like QML. There are other like suggestions for having hybrids, classical models, etc. But I think of this as, okay, this is smart. This is really smart way to build something on top of like the quantum knowledge that we have. And then when it comes to drug discovery and molecular simulations, so my actual research right now focuses on quantum chemistry and error correction in quantum chemistry. And the thing that we are sure about is that in quantum chemistry, there are problems that are really unsolvable using classical computers. So in the first glance, we know that this problem is not solvable using classical computing. Let's try to solve it using quantum computing. So the approach is starting in the right way, where we do have this advantage that we can claim at the end if we manage to create the right algorithm or come up with the right algorithm. And then in sustainability and climate change, I've been like reading several papers that come up with like quantum machine learning approaches to, for example, for grid or energy grid management, and then resource estimation and logistical optimization. There are many algorithms that shows good accuracy, good results, but still the approach or the architecture of these like algorithms and approach is not like quantum machine learning. It's just like hybrid inspired. Because they need like to show the practicality of this. So they need to have large amounts of data. And with a large amount of data, it's going to be quantum inspired hybrid and not fully quantum machine learning. But there is some exciting applications for quantum machine learning, because we know like we have AI, we have machine learning. Inside machine learning, we can have something called natural language processing. Natural language processing is an emerging field. So all of the hype of the AI that we're getting today from like the large language models is based on NLP basically. So the approach of quantum NLP, I see it also as a clever way to approach quantum machine learning. So I don't know if any of you here are familiar with the Oxford team. That Bob, he's a really famous researcher. He's like a British researcher that came up with Lambic. So Lambic is a library that does quantum NLP very differently than classical NLP. So the way that we do that is like we transform the data, which is like a classical data, into quantum data very differently than we do. For example, it's not the same approach of like, I'm just encoding the classical data using amplitude encoding or like angle encoding, and I'm sending it to a quantum or sort of CNN to do the prediction or the classification, but in the way of how we really encode the data. So we use something called the CCG grammar, the combinatorial categorical grammar. So this is another way of approaching text data. So instead of you using like vector embeddings, we're going to use something called string diagrams. And the string diagrams are transformed later on into quantum circuits. And these quantum circuits is surprisingly that you can have the same accuracy of like a classical model. Well, the example is really famous. You can find it also on the Lambic like websites. It's a penny lane package developed by this team. So you can have the same accuracy of like a classification problem with only 300 line of data. So you can train Gen AI like LLMs with very small portions of data using the quantum NLP, but it still has a lot of limitation when it comes to the string diagrams and the circuits that we create, because we need to transpile these circuits. We need to do a lot of work with these circuits to be able to get the results at the end. But you think of it as if you're like representing the words inside of qubits, and then the wires or to capture the semantic knowledge between the words, you're gonna use entanglement. Just think of it this way. But the approach is really interesting, and that's actually what we are doing at Qatar Computing Research Institute. So we're trying to do quantum NLP for Arabic language, because for now Lambic is only provided for English and Japanese. So we're trying to do it for Arabic language. It's a really hard task, because we have a lot of things that goes with the Arabic language, like tashkil, and then one word that have the same like letters, but it means like different meanings when it comes to encoding this. So the potential advantage here is like if we have 1 qubit, that qubit can encode all the meaning of the same word. So instead of you having that big data set that will encode all the meaning of the word, and then like it's thousands of lines of data, you will have like only one input or 1 qubit that can be measured several times, and they can, with every measurement, it gives you another like data point. So this is really exciting. I see this as a potential use for QML, right? Because we think of how can we really approach the quantum machine learning problems or the classical machine learning problems in a quantum way. That's the aim. So there are several types of QML approaches. As I said before, I disagree with some of them, but we have them, and we have a lot of papers that have been published on these approaches. The first approach is the quantum enhanced machine learning. So here we're using quantum systems to improve machine learning. We have different variants, the VQC, the quantum SVMs, the quantum neural networks, K-means clustering. So these are variants of classical algorithms that has been developed in a quantum way. We have the second type, which is classical machine learning for quantum tasks. And this is actually really important because as Hani, I think he presented before me, he mentioned that anyone can jump into quantum computing even from like a pure classical background. Because what happened with DeepMind and Google Quantum AI is like in the new architecture of the Willow chip of Google, they have been using like classical reinforcement learning for error correction, and they have reached below threshold. And this was a fully classical contribution of machine learning in quantum computing, which is something exciting. So you don't really need to know about quantum computing to be able to contribute to the field, or quantum machine learning to be able to contribute, because you can do that even with like your classical machine learning knowledge. There is also like, for example, for the IBM Qiskit transpiler, they are also using classical machine learning to optimize the circuits, to transpile the circuit, which is something really fascinating. And then we have the hybrid models like classical plus quantum mix. And this is like a really open research area where people are trying different architectures, like some quantum layers, classical layers, trying to improve the accuracy, to improve the precision of the models. So this is like the paper of the alpha qubit. It is an AI-based decoder, and you can check the paper. It's been written by like a big number of like scientists from Google Quantum AI and Google DeepMind. So they were able to optimize surface code and then reduce the noise in the current superconducting computer for like the Willow chip for Google. And then there are also some like interesting research area in quantum machine learning that I found them. I think it's necessary to jump in this area and try to investigate the potential of quantum computing. The first is mathematical foundations of quantum machine learning. Quantum machine learning has existed since years. We had the math behind, classical machine learning has existed, and we had the math behind classical machine learning. It's all working well. Now it's time to come up with QML foundation, mathematical foundations for QML, like exploring the kernel theory, the geometry of quantum machine learning models, etc. We do have also explainability in quantum machine learning. This is an area, I think recently some people started investigating explainability in quantum machine learning, but it's a very open research question that we are facing in classical machine learning, that we need people doing quantum computing to jump into this field and try to help. For example, we have the ability to visualize the circuits, to understand like the learning features, the transparency in like hybrid quantum classical models, etc. So this is really important. And then we have causality in QML. So causality is also like an open research question in classical machine learning that we need to address using quantum computing, because there is a potential. We do have like phenomena that does not exist in like classical machine learning. And then there is also cryptography in quantum machine learning. So there is like an exciting announcement at the end of my presentation. That's why I didn't add like a lot of explanation here, but there are really exciting projects that are ongoing. It's really recent approach to tackle quantum machine learning from a quantum communication perspective, I would say. So just to go quickly through the QML pipeline, and this is like for the students basically, because I believe that you will be trying to work on some VQCs and VQEs for your quantum solutions. So the quantum pipeline is really easy, really straightforward pipeline. So it goes from like classical data to quantum data, and we try to like map the large Fourier space of classical data into a quantum Hilbert space, do some pre-processing, build the quantum circuit, and do the post-processing to do the measurement and get the results. So there are several ways to do quantum data encoding. There are these three like known, and there are many ways to do it. So we can do it using basic encoding, angular encoding, and amplitude encoding, though this is very costly. This one is really costly. But when we think about data encoding, as I mentioned in the beginning, we have the noise and we have the limitation in terms of number of qubits. So these are all like problems that we are facing when it comes to data encoding. And then we have the quantum models representation. So the actual approach of quantum machine learning is like, instead of us using neural networks and weights and layers, we're just using parameterized quantum circuits or PQCs with like gates, and we're just like trying to tune the parameters over the weights. And then this is like the ongoing process of learning for the quantum machine learning model. And then the exciting thing is like, for example, for the loss function, we always do it classically, which means that we're not even doing quantum machine learning here. It turns out to be classical machine learning always. For the learning processing quantum machine learning, so it's like a forward pass. So we just encode the data, parameterize the circuit, do the measurement, and repeat it again and again until we train the model. By defining like the loss function and doing that classically. And actually, we try also to avoid backpropagation in the learning process, but this is also like theoretically it's been done, but like in practice it's not that much feasible. So the training is also interesting to see that there are several ways to train QML algorithms. So we have the VQCs, we have the kernels, and we try to do fully quantum training, like quantum backpropagation. So there are papers about quantum backpropagation, but we still a little bit far away from getting it into reality with the noise. So there are several limitations. I hope this presentation was not really like pessimistic presentation about quantum machine learning, but it was like, this is the reality. We should know that, we should witness that, and then we should think of how to solve these problems. So we have the barren plateau, which is like a problem that Dr. Allen mentioned when it comes to using VQEs. This is a way, if we have more data, then we can never scale with VQEs. So this is not the right way to approach it. We have the dequantization, that classical catch-up. So there are several better algorithms that exist in the classical world that we can never beat them using quantum machine learning, because quantum machine learning has not been set to solve these type of problems. And then we have the data, the problem of the data encoding, as I mentioned before, and the exaggerated speed up. So we always aim to have this speed up of the quantum algorithms, but we still need to think of it in a quantum way. So there are several frameworks that can help you to do QML. There is Penny, there is Qiskit, and there is like some other libraries that exist, for example, Circ from Google. So you can also play with QML a little bit and create your circuits if you want to. This is like for the Hackathon students. And then I want just to end this with like this presentation. It was a technical presentation, but I just wanted to mention some of the efforts that we're doing. Like almost 1 year ago, we created Quantum Africa, which is an NGO. For now, we have 127 members from almost 25 African countries, and all of them are motivated to contribute with no cost to the quantum African ecosystem. So if you're interested to know more about Quantum Africa, you can just scan the QR code. If you're interested to be a part of Quantum Africa, you can also show your interest and then apply. We'll be happy to have you. Also, like Walid, my co-founder, is here, so he's one of the mentors. So if you are interested to have a discussion with him as well about Quantum Africa. And then this is the exciting opportunity that I wanted to mention concerning quantum machine learning or cryptography in quantum machine learning. So there is this open call for like 2 PhD position in Johannesburg in South Africa. So this call is from the AIMS, African Institute of Mathematical Science. So the project is led by Dr. Ryan Swicki. He's a really quantum machine learning, quantum physics person. What is exciting about this is like the project is really innovative. So the question that they are trying to answer in this PhD is like, can quantum computers provably offer meaningful advantages for quantum machine learning or machine learning? If not, can one prove their limitations? Can one develop provably efficient algorithms for learning about quantum worlds, like learning the unknown? And then how can quantum cryptography be utilized to provide cryptographic advantages in security for the state-of-the-art ML algorithms and models? So it's a really interesting combinations of like quantum machine learning and cryptography. And if you're interested, you can apply. So the call is still open and the project is really exciting. And yeah, thank you so much. If you have any questions, feel free to ask. Okay. It's like my perspective on quantum machine learning. I see the fact that we realized that we are doing it wrong. We started thinking of other ways to approach quantum machine learning. So if we went back to the fundamental level of like tackling math and then really important problems in classical machine learning, we're gonna do it right. Otherwise, it's really far from being like or having the real actual quantum advantage right now.
What's your scale that think it works better, best with quantum machine learning?
For the VQE or it depends. So I never measure the model that I'm creating based on the accuracy or the data that I'm using. I really want to show up the quantum advantage. So if I'm using this small portion of data and I'm trying to compete with another algorithm that exists classically and that are using like terabytes of data, this is not real quantum advantage. So accuracy is not comparable. Because if I use the same amount of data on a classical machine learning algorithm, I would never get the same accuracy. So the comparison is not fair at this moment. Yeah. Thank you. Thank you. Okay, that's a good question. So what's your major? Is it physics or AI, computer science? I think you have all the chances to start diving into quantum computing just by leveraging the knowledge that you have in AI to solve problems that are related to quantum computing. I think like quantum error correction right now is highly related to like classical AI. So this is like one way to start in it. And then there is like many courses available online, like Google, IBM, all they provide really good courses to start preparing. Yeah, good luck.
Now the talk for Jan Plumart. Jan Plumart is the managing partner at Biodec, which related to or which give us a data analysis center for life science. Also, in BioDAC, he leads a team providing advanced data analysis solutions. Today, he will talk about business, about cost of planned and unplanned downtime of IT systems.
Good afternoon. I'm really honored to be here. And I'm very positively surprised, a bit over by all the activities that is going on in Egypt and in the wider Africa continent. I have two talks and I'll combine them. One is about the project that we are doing with Dr. Taha. It's about X-ray astronomy, and that has, I would say, quantum content. And the other is about security and what goes wrong in the world today if you don't care about security. And then you have a lot of unplanned downtime, I can tell you. Talk without microphone. Is that okay for you? Thank you. Maybe that's easier. Sorry? Yeah, but it's there. I've downloaded it or uploaded it, but it's not showing on the screen. Unfortunately, I don't speak Arab or one of the country versions of Arab, which is such a universal language. Obviously, I knew that, but now I see the practice of it. And it would be really good if we could help with your quantum advantage.
Is this part of the presentation having this downtime?
It's unplanned.
It's part of the quantum or the question. That's a good question. Yeah.
In the meantime, let me try to make a connection. One of the famous historic facts is when the astronomy started. It was, let's say, in India and in what is now Iraq, Iran, and Arabia. And it's therefore good, I think, that we start with this project. It's about X-ray astronomy. So in the cosmos, you have phenomena that make radiation, electromagnetic radiation, and some of the most explosive phenomena cause X-ray radiation. Good. Thank you very much. So, and we do this project with an institute of a research company in the Netherlands, which is called ESROM, and then with Taha and a few colleagues, and then one or two people from my company and myself. So what we have, this is a star or a black hole, yeah, with a lot of dust turning, and you have extreme phenomena in the center causing these jets. And this such an object in space could be or will be a source of X-ray radiation. And obviously, there you see the normal electromagnetic spectrum, the whole window of frequencies. And somewhere you will find more on the left side, the X-rays. So there are satellites in space with special detectors on top of them, and they detect the X-ray photons. Now, this is then the kind of spectrum you receive, and you will need to detect the peaks and assign the peaks to elements and particular electron state transitions in those elements. So far, so good. This works fine with classical computing. However, what is going to happen in coming years, there will be new satellites, one or two, with an extremely improved energy resolution. So the number of peaks that you will see in such a spectrum will be 100 or 1,000 times bigger, or even more. And on top of that, the number of images that the detector on satellite will make will go up as well in similar order of magnitude. So there is the complexity of the analysis of such a spectrum and the volume of data that needs to be investigated. And we are pretty sure that it will be very difficult on classical computing. So here we are investigating in this stage the use of quantum computing, also possibly quantum machine learning, detect peaks. And another aspect is that we will model ions, electron states in those ions and atoms up to pretty high elements using quantum computing. Because we have good reasons to believe that we can improve the accuracy of the calculations of the outcome, which will help us to do a better analysis. Also, there's another aspect. Such an object in space is pretty far, and the photons coming to Earth, coming to our satellite, will pass what is called interstellar media. And there are dust and particles and other things that absorb or reflect these photons. And in that area, you will find exotic small molecules. Yeah. So there's another area where we can model those little molecules using quantum computing. And we all know that there is a natural fit for that problem. So that's another area where we active. So no publication yet, but a lot of activity. Any question on this subject? Because now I have knowledge. Yeah, I mean, this is the form of such a spectrum. Yeah, there are. No, it's the form is pretty explainable, I would say. What the difficulty is for all those individual peaks also have a form, yeah. And so you need to, yeah, you have all those peaks that are on top of each other. That's so you need to define what I would call the fingerprint of an individual, and then do adding up of the rates because they are all what do you call it? Decay rates. I don't know what you mean, but actually one is like very common. Yeah, but maybe this is a kind of spectrum that belongs to one kind of source. But in the cosmos, you will find different kinds of sources that all produce X-ray, and they will have different spectral images. Like in terms of having some sort of on advantage, might have better flow, right? And you have some heteroscedasticity. Yes, closer to the initial. Might get to this is one. Well, I mean, in our initial thoughts to deploy quantum computing had to do with improving the accuracy of the predicted action. The secondly has to do with predict the decay rates of the electron states for heavy elements, which is pretty difficult in itself. I mean, it's all relatively easy if you have a small atom with 2 or 4 electrons. But the difficulty is when you have big atoms and all kinds of elements. Okay, for now. Yeah, well, it's yeah, and up until now, the energy resolution of the detector on the satellite is relatively bad, so you don't see many peaks. Yeah. But for the next generation, we will have a vastly improved energy resolution, plus many more images per time. So that's and the improved energy resolution will give you many more peaks, many of which you cannot assign easily to one element. So that's the problem we're gonna see in the coming years. Okay, now I need the second. Right. I have to be honest, I took a few slides from IBM from a month or 2 months ago. No, but here is something, and this is, I mean, I'm from the Netherlands. We think we are a civilized country, and most of the things are working okay. However, this has really happened. for the others and for recording. So good point. I'll repeat. I'm from a nice country, well behaved most of the times, and healthcare is okay in our country, and in that regime we have what we call regular surveys to detect to reach early detection of potential cancer. Yeah. So people every 2 or 3 years or every 4 years they get a letter and they can go to do the test. Yeah, and then later on via some lab and they get a letter, it's okay, or you need to go to your doctor or the hospital. Now what happened here is a relatively famous lab. They got an invasion from some bad actor, yeah, and they have been copying, unloading enormous amount of data of maybe 1 million patients of the last 10 years. And that in itself is an enormous disaster. But the problem is, what will happen with the data of those people? Yeah? It could, because they are for criminals available on the dark web. Yeah? And then you get misuse, potential misuse of personalities. Yeah? But the thing is here, they have collected unique identifiers of those personalities. Yeah. And in our administrative system, there is only one person with one unique identifier per patient, per inhabitant. Yeah. So what I mean, I'm really wondering what's going to happen. And I'm showing this, it's a real example. And I'm sure it will happen many more times in many other countries. But this is consequence, and it's happening today. Yeah? Not in 10 years, not in 5 years, when the quantum computers are potentially strong enough to break our current encryption. Yeah? But it's really important. And everybody should be aware of this. And another problem is the consequence of this disaster may be that people don't want to go to such a test anymore. Yeah, so that has bad consequences for public health. Yeah? People lose trust in the health services. Yeah? So that's really bad because the reputation goes up. Yeah. Sorry. So here is some other. I mean, it's public. I'm not showing secret data. And there are many people, the number is much higher now, who are going to go for legal action, obviously. And yeah, I'm really wondering what happened and what is going to happen. Anyway, so this is important. That's security, really important. Then there's another aspect. This I took from IBM. Yeah. It's the increasing complexity. Yeah. So what we are seeing with all the tools, all the kits, all the means that we all get everybody can develop applications, yeah, in one way or another. So the complexity of these enormous numbers is going up and up and up. And that's, you cannot keep hold of it on an individual basis. Yeah? And I mean, AI is a typical example of this, obviously, but everybody, you can build your own little applications on your smartphone. So the consequences of this is that here's the problem, because we all want service now, yeah. Whether I'm in the Netherlands or in Egypt or Alexandria or some of you in Abu Dhabi or Riyadh or wherever, you want your service now, yeah. In the evening, in the morning, at night, you want it everywhere immediately. So how at all can you manage it? Yeah? And so the IT departments, companies, or also universities, yeah, they need to, how do you manage it? How do you do maintenance at all? Yeah, because all the applications, whether it's for banking, for travel, or for scientific research, or quantum computing, yeah. So there's an enormous problem. Then, well, I'm only talking about classical intrusion, yeah. And how do you do your unplanned downtime? Yeah. Now here is only one answer, and we need to talk about it. It's what I would call maximize automation, yeah, with maximum use of AI. And it has to do with the cost, yeah? The cost of not doing it. Yeah? If you do it in a classical way, the people, the staff must work at night or in the weekend. Yeah? You lose revenue, or the students cannot do their homework or their examinations. Yeah? So this is what I want to address with you. Maybe we can have a little talk about that. This is it. So, X-ray astronomy. Students who are interested, we contact us, Dr. Kao and myself. And for this we can talk about what we want to do. All right? Thank you. Yes.
Okay, now the talk for engineer Sameh Zaghloul. Sameh Zaghloul is a CTO and digital transformation leader at Fixed Solutions Group. He also specialized in architecting complex enterprise scale solutions, and his talk today about quantum risk assessment. I am really interested to know about quantum risk assessment.
Assalamu alaikum. Actually, this session actually is complementary to the risk part, actually, the opposite of quantum computing. Okay, so it is coming. Okay, so we need to be prepared. This is actually the main point. So what we are discussing today actually is quantum safe future, simply assessing quantum risks, current and the future. Future, you know all about future risks actually, but what about current actually? We know actually. This is not only happening currently, actually, it started happening couple of years so far. And the transition, this is the challenge actually. This is a complex migration project for critical infrastructure. So this is a very complex migration for infrastructure. Okay. Briefly, what is that three side of quantum security triangle actually? Okay, let's imagine that we have our data actually stored in this vault, say, okay. In order to keep my data safe, actually, we need three things, actually. And this is actually the three sides of quantum security. Actually. First part of how truly random generated keys I use in my encrypting the data. So this is we call true random number generating, which we can use quantum technology on it. So first one actually is to use real random keys. This is the first one. Mandatory actually now actually and 20, 30 years ago. So this is mandatory in all cryptographic system. True randomness. The second part, this is related to the evolving power of quantum computing is to use post-quantum resistant cryptographic algorithm. So instead of RSA and yes, and all famous algorithms that we all use in our own application currently as we speak, in this live streaming, actually use RSA, for example. Okay, we need to migrate this actually to another category of algorithms, actually, that theoretically, quote unquote, should resist quantum computing at the Q day. The third important part is quantum communication or quantum key distribution. This is the sessions that already Dr. Salim Hajjaj actually talked about. Okay, I need actually to secure the transmission of the keys. Actually, this uses quantum technology. Okay, this is sorted by difficulty. Actually, this is the most complex part, but this is the future of quantum security. Actually, quantum key distribution or quantum communication or quantum cryptography. Okay, but this need dedicated actually quantum hardware, like using photonic chips. Actually, like Dr. Salim was mentioning today. The second part. This is post-quantum cryptography, actually migrating to post-quantum algorithms. Actually, this does not need quantum hardware. This should be done. The only way to be done actually in our classical system now. So this can be started actually immediately, today, yesterday, 2 years ago. Okay, so we don't need anything actually to start implementing this. And the easiest one is to use a true random number generator or quantum random number generators. And this is commercially available. Personally, I know at least 10 companies worldwide actually produce this quantum random number generator hardware. And this is something we can produce in Egypt, by the way. This is something like ASIC chip, but photonic. It does only one thing, actually, it generates a continuous random sequence of photons. That's it. But this is very easy to manufacture. No. And this is what we can start with. So this is to summarize actually the 6 things that we need to have a complete security. Okay. Q day, this is actually coming within few years. Okay. This is the time actually when the power and qubit count of quantum computers actually will be enough to break Shor's algorithm for RSAs that already developed 30 years ago, or the equivalent algorithm developed, I guess, something like less than 1 year. So we have actually, since last October, the equivalent for Shor algorithm for ES. So actually, all algorithms are there, just needing actually the right power. We call it the cryptography relevant quantum computer. Okay, and this is not new news. Actually, this is published by at least 10 years now by NIST. The type of affected algorithms. Actually, this is published 9 years now. And this is a problem statement that we are talking about. Okay, there is a theorem, very, very nice theorem, Mosca theorem, x plus y. If x plus y greater than z, actually, then we have a problem. X is the migration time of my critical systems. Okay, y actually is the life shelf actually of the data that I'm protecting. And Z actually is the here. So if I exceeded this, actually, so my data is exposed. But this is in the Q day. Does this mean that we are secure for now? Let's see. But before we go to the migration, actually, this will not happen for the first time. Why? Because we have been there before many times, actually, since the start of cryptography in 70s. At least there was something like 8 migration milestones actually for cryptographic algorithms migration. So this happened many times before. This is migrating for post-quantum cryptography. Actually, this is not something new. Actually, okay. The impact will be a little bit larger or huge, but this happened before. Actually, at least 10 times actually through the journey since 70s. Okay. So again, we are talking about transition to a new family of cryptographic algorithms or cryptographic security. Okay, and we need to do it now. One important point, okay, regarding post-quantum cryptography algorithm, and this is actually this comment was mentioned by Dr. Ahmed Yunus many times before. Okay, this is work in progress because we have a standard coming from US NIST FIPS 203, 204, 205. Okay, this was published, I guess, less than 1 year. And this is equivalent, actually, work actually done in the European Union and equivalent work done in China. Okay, of course, work done in China is not published, of course, for sure, for many reasons. Okay, one of the reasons, actually, one of the published reasons that they will not use any quantum cryptography standard from US or Europe because they are not sure actually it is really secure or not, which is valid. Okay. The other important thing actually is this, and this will relate to something called what we call cryptographic agility. That okay, if next year actually we have modified version of FIPS 203-1 or -2 or -3, actually, what I should do. So I need actually to migrate to an agile system such that any new cryptographic algorithm actually could be plug and play without redoing hard migration once more. Okay. I'll start with threat actor, not today, but Q day. Okay. This will happen in Q day. This is what we expect to happen. Okay. The threat actor, okay, will get the encryption keys and will get the encryption data, and using quantum computing with enough power actually can already decrypt the keys and the data and access my data. Okay, this is clear. Okay, what about today? This is a threat actor today actually. Actually, not today. Actually, this is at least 3 to 5 years because the term harvest now, decrypt later started to appear actually 4 or 5 years ago. So this is what is currently happening worldwide. The threat actor, okay, is capturing encrypted keys and encrypted data. Can he already decrypt them now? No. Okay. He just stores them and will decrypt them later at the Q day. What does this mean? Okay. If my data will be valuable or critical after 5 years, assuming that Q day is 5 years. Okay. So someone has my data now. Okay. And can decrypt it 5 years ahead. This is risk. Okay. If my data actually, shelf life of data actually is more than that 10 years, for example. So is the Q days 10 years, so it's the same actually. If my data actually is shelf life actually 1 year, so I don't need to worry. And this is part of quantum risk assessment. So part of assessing all the criticality of this is assessing the criticality of my data and the shelf life. And this bring us back actually to most criteria actually. The migration time, which is not trivial. This is a huge effort. And the shelf life of data. This plus this. And this is the time actually to Q day. In other words, actually, what I tried to say actually is everyone in the world actually is doing this on the other countries, either countries, organizations. Okay, so actually this is started actually, and we are at risk since few years now. So when we need to take action. As a Q day, yeah. After the Q day plus 3 years. Exactly, actually. Okay. So what we mean by quantum risk assessment, we need actually to build what we call cryptographic inventory. Okay. I must know actually what cryptographic inventory I'm using in my system. Okay. Then also the PKI health check. My PKI infrastructure, the systems that I generate my keys actually, private keys and public keys. PKI, our certificate authority. Okay. And also actually, we need to do post-quantum risk assessment. Risk assessment actually, what is the value of this data? What is the criticality of the breach? So I built the plan and the roadmap actually based on risk and cost. This is the risk assessment mainly actually. So start with immediate fixes actually and short and also work on the long term. Okay. We have many of classical encryption algorithms actually in all the layers of the system: symmetric, asymmetric application, hash functions, key exchange protocols, digital signature, and all the server skills that we are used, and all the cryptographic libraries actually that we use currently. One good thing actually related to open source. One of the advantage of the open source currently is almost 99% of open source stacks in all applications without exception, like OpenSSL and OpenVPN, has migrated already to post-quantum algorithms actually since something like 1 to 2 years before. So already. يعني actually the NIST competition was running like 5-6 years now, and there is multiple candidates. Many times, yes, this is exactly the cryptographic agility. So actually, I have OpenSSL version 1.x, okay? And version 2, actually, I have, we had 2 years ago, the first version of post-quantum cryptographic algorithms. And every couple of months, actually, we have a new version with the enhanced protocol. Exactly. And this is exactly what we mean by cryptographic agility. I don't need to migrate everything from scratch. This will be just as normal upgrade. The challenge is to do this actually for complex systems. This is not an easy task, believe me, actually. Okay. So what is the order of magnitude actually? What is the effort, the level of effort actually that we should expect here? For example, if we take a medium-sized data center, HVM or Docker instance or whatever, or server, will have typically from 20 to 50 distinct cryptographic algorithms with different flavors from the previous slide actually. So I can have 5 or 6 versions of RSA in different layers of system. So this will not be considered one. This will be counted as 5 actually, because I need to handle each one separately. So if we have actually in the medium data center, I'm talking a large enterprise with critical data, 100 servers, actually you are talking about hundreds of cryptographic algorithms. So first part actually is to know what I have and inspect all the layer of the system and get a detailed inventory. There is no one tool actually can do this automatically. No, I need to use mix of tools because we have starting from the user layer application, a web layer, application server, middleware, integration service bus, API layer, database operating system, networking, storage, all this layer actually, the 7 layers, the classical 7 layers. I need to actually to check each layer thoroughly, and also the code. So multiple tools must be used in this, from static code analysis, dynamic analysis, runtime applications, and network traffic analysis, which is very, very important. Okay. Configuration of system scanning on all levels, okay, for system handling, and dependency analysis, which system call what systems, and also cloud environment scanning, either public or private, and hardware and firmware analysis. This is very important, including servers, storage, network, firewalls, IPSs, everything. I need to check the firmware actually for all my devices in all categories, and also certificate and the key management. This is very important, and the log analytics like SOC solutions and stuff. So it is not an easy task, but it is not impossible. Okay, this is take a lot of effort and multiple teams actually, because the main challenge here actually when we started this services or this exercise, that we need multiple skills actually: network team, system operation team, infrastructure team, security team, application team. Okay, combine the team actually to gather all this information. The target is to build what we call cryptographic bill of material. Cryptographic bill of material is simply some standardized form actually. It is open source, and by the way, actually historically it was both open source by IBM actually a couple of years ago. Many organizations use it in collecting actually, or this is de facto scheme actually for collecting cryptographic data. Okay, so CBOM actually is our target. This is actually N1 inventory system. I need everything: system, application, IoT devices, all the devices actually on layer application. And we have a holistic overview of my cryptographic landscape, mainly for enabling risk management actually. So I need to track this cryptographic inventory at the progress done on each step. Okay, and review our readiness. There is no standards actually put currently so far, but in Europe, for example, and US as well, they are talking about something like all current cryptographic algorithms cannot be used after 2030. Cannot be used. So, but should I wait to continue using this to 2030? Actually, this is one of the discussions that we need to discuss today, because we read this actually. So I need to stop using this today actually to save money after 2-3 years. Okay. So this is a very simple example for a sample cryptographic bill of material. Something like web server, Nginx, this is open source, very popular. This is the cryptographic algorithm. Okay, the library used OpenSSL, which is a good, okay, because actually OpenSSL and TLSL are both quantum ready now. An example: backend API using JWT or Java Web Tokens. Okay, this is using RSA. Okay, we should prepare actually for using, instead of GWT, PQC GWT, for example. The same for databases, mobile application, cloud authentication system, login services. The main thing here actually, we started doing an internal pilot in our systems 3 years ago. Okay, so the conclusion actually is that all open source components actually we could immediately, with almost minimal effort, actually migrated to post quantum cryptography. Commercial components actually still, like for example, I have a firewall from vendor X or commercial database from vendor Y actually. I am depending on them, unfortunately, because they are not moving that fast, because this need longer cycle of development, testing, deployment. This cycle is much, much faster in open source. So open source actually is one of the recommended strategies actually to be ready for the quantum era. Okay, what we need to do, QD plus 3 years. is hybrid approach because this cannot be done in 1 week, 1 month, 1 year. Okay, so I need to start with assessing what I have. Okay, and fix the quick actions that I need to implement immediately and both long term. Okay, and keep continuous monitoring actually for all the components, all the system I installed, like my previous section actually 1 billion applications. This new application actually at least should be post quantum ready, just to avoid going in this critical migration path. Okay. One of the examples, quick examples for hybrid approach is data at motion. We have actually data at motion and data at rest. If you notice, actually, actives here actually is focusing currently on data in motion. Okay, transmission over the network. So this is the media part I should focus. Okay, data at rest inside my data center storage, so a little bit difficult actually to take the encrypted data from disk, but at least doable. But the immediate risk is to secure data in motion. Okay, and one of the approaches that we already implemented in current 2 projects so far is what we call post-quantum traffic proxy. So the traffic actually is coming in the application layer. Okay. And already communicating everything using HTTPS and TLS1, okay, and using RSA. This is not post-quantum ready, okay. So what we can do actually is just put a proxy layer on front of my web servers and application layer with post-quantum cryptography enabled, and this will be as umbrella actually surrounding my interaction, my system with the external world. So this is a quick fix and can be actually biased couple of years, by the way, to the final migration. So the hybrid approach is recommended. The last yes, this is the last slide. Okay, this is mainly actually what we should do in general. This is not a short-term program. No, this is a hybrid, short-term, mid-term, long-term, mainly. Short-term actually is doing the cryptographic inventory and risk assessment. This is a couple of months. Actually, this is a lot of work, but this is not impossible. This is possible, doable, and must be done, because without it, actually, I will not know my risks and do the quantum risk assessment. Risk assessment, what I should do first, at what cost, at what criticality. This is very important. Okay. Then midterm, like the next couple of months to the end of the year, pilot migration for key systems using hybrid approach, for example. Okay. And then the long term, which is typically couple of years. So this was in a nutshell, actually, the how to be ready for the risks of quantum computing. Any questions? Okay. Okay. I split it in 2 actually, but okay. One thing about, we are talking about software or middleware, right? Okay. So at least there's okay. By analogy with pen testing, penetration testing, or security assessment. Okay. Yes, exactly. But okay, what we can do, yes, I'll bring this because this is the reason for this slide, actually, the vault and the triangle. Okay, there are 2 things that we can do now immediately without any problem. Okay, first, actually validating the true randomness of the keys, and this is not related to quantum, by the way. This is actually NIST started to talk about this actually like 25 years. So we have NIST special publication 822. This is something like 22 years, something like that. And another one overrided 800 special publication, also 890B, 15 years ago. newer. Okay, so this was actually this set of statistical and the cryptographic tests actually to test the true randomness of my keys. This is doable. It used to be done actually in all critical systems before quantum computing, and we do it now actually on quantum. So this can be done now. No, the keys actually are totally random. This is the first side of the triangle. Okay, the second side I can check actually the used algorithms. Okay, but yes, as you mentioned, I don't have enough power actually to test it. It's really random. That's why actually I put some stress on cryptographic agility and OpenSSL example. Okay, so OpenSSL, for example, is post-quantum ready. Why? Because it uses actually one of the Nest FIPS protocols, right? But am I sure that it is really post-quantum ready? I'll keep testing actually each month, each year actually, okay? And I should be able to upgrade this to the newer version, okay, immediately. So this is, can answer this because yes, I'm not sure. I answer third part actually. This is the part related to quantum key distribution or quantum communication, okay? And this is the topic of Dr. Hisham Bado yesterday and Dr. Salim Higazi today. This is a little bit tricky, okay? But can be tested, by the way. Yani actually, one of the solutions that provided by the way, China is number one in this area, okay? And everyone in the world actually behind this. But all other solutions in the world actually provide you with simulation key. We call it sometimes Eve simulator because actually we install the two boxes for quantum key sender and receiver or encoder decoder, okay? And a third box actually to simulate intruder or eavesdropper, like Eve, for example. And we can test actually the impact. So this can be tested, but a little bit expensive. So the answer is a little bit can be split to three areas. The second one is post-quantum cryptographic algorithm is work in progress, but we should be ready actually because this is part of life. I hope I could answer. It is very difficult question, by the way. The second question, sorry.
What can please help and us each other with the arguments?
Yeah, quantum key distribution is a special case because the encoder decoder actually should be from the same service provider. Upgrade is outer layer. يعني the example, for example, the example. Exactly, because this is a critical or tricky migration project. So by the way, actually, I'm working in IT for many years. A migration project actually is the most complex project actually, and especially post-quantum cryptography. But I'll start with one example of the proxy layer or the hybrid layer using the web server. So if I upgraded the web server in one component, actually, I should upgrade it on the other side. So this must be planned. But this is typical business as usual, actually, for migrating critical systems. The dependencies of the system. So this is business as usual, actually. This is how we do it. It is complex, but it is doable. I hope I can. Thank you very much. I start with only one thing, actually. I'm an engineer, by the way. I work in the field, actually, practical hands-on experience for many years. So I usually, what I learned actually, so put one simple target and achieve it immediately. So I will start with only one thing. All new systems actually should be, will go live actually starting from today, will be post-quantum ready, full stop. There is a 9 items in the list actually, but I'll start with this. No, actually, as a remaining, actually, will be something like this, putting this actually, because this is a very complex. So, for example, Biden has issued a mandate 1 year before he leaves, actually, that all federal government should complete post-quantum readiness assessment. Okay, this did not happen till now, by the way. So, for example, so it is a little bit challenging even for modern countries. What is call it? Something. Uh, yes. Yes. So cryptographic agility again actually is one key actually, and this is from my side actually. This is what I see value actually for my background as a solution architect, complex solution architect. Is this achieving this cryptographic agility in complex systems, because I'm not talking one component, actually many components integrated and interconnected. Okay, this is good question actually, and let me clarify actually, not necessarily quantum random number generator, but this is actually this is currently available and much faster. Okay, but usually 10, 15 years ago, we had what we call hardware called TRNG, True Random Number Generator. What it does, okay, is two things actually, using the pseudo algorithm to generate the keys, and secondly, actually integrate actually external random phenomena like external noise, external humidity, whatever actually list of at least 10, you measure at least 10 random external variables. All of them, you must not have any control of them, and you mix all this actually pseudo algorithm and is actually random phenomenon actually and produce true random number. Okay, but to make sure, you need to apply both statistical entropy tests. Okay, and this actually pseudo random numbers can pass this test, but there is other variant actually. I can actually show after this. Just yesterday actually was talking. Was testing actually something like called Die Harder. Die Harder actually new set of something like 25 statistical algorithms actually was developed actually to override NEST 822 and NEST 890B actually, to make sure that okay, this is truly random, will pass the randomness, the chi-square, all this actually, okay, and also cannot be reproduced or predicted. You should not be able to control this. This is the trick. You can measure this to make sure, but the main thing here actually is you should not be able to predict actually what will be generated. This is okay. Monte Carlo distribution actually is one of the statistical tests, okay? But this is not enough, actually. There is something like 20 other tests, actually. I can share with you, actually, after having my laptop, because constantly I was working on this yesterday, because this is part of the project that we are doing. We use quantum random number generator to generate the code, but I must make sure, actually, that the codes actually are truly random. and this is classical problem before quantum computers. Okay. True randomness is totally separate issues, and it is a must actually in all cryptographic solutions. Okay.
Now the last talk to Dr. Sharif Farid. Dr. Sharif Farid is a nanotechnology researcher at the National Research Institute of Astronomy and Geophysics in Helwan. His academic journey is built on a strong foundation from Egypt's leading institutions. His talk today is about researchers' role in localizing industry. Welcome.
Assalamu alaikum. Good evening. I would like to express my thanks to Dr. Taha and to all the organizing committee here in this great place. I'm very happy to be here with our professors and with all of you. As you know, we'll talk about the role of researchers in localizing industry. And actually, this talk is mainly for undergrad. But in the same way, in the same time, sorry, I will be grateful if our professors give us any supportive ideas. Simply now, why a businessman or industry man needs help from researchers? Simply because they transform an idea to something useful for them. You all know the needed sequential steps for any research work, okay, as we see here. But today we will reflect them on industry. Okay, you know, the first thing the first step you do that you identify the problem. Okay, how we precisely identify our problem with a product or something. Let's see here a very simple example. Imagine with me that we have a room here, a guy living in a room, and he has here electrical heating element, electrical heater here, okay. But after 1 month, this guy became nervous because of the electricity bill. Okay, he asked us to find a solution for this problem, for example. As we said in the first step, we have to identify the problem. And we do this how? In many cases, this step is not easy. Why? Because it depends on how many disciplines are involved in this. In this case, the heating element, the electrical heater itself, represented, we call this a system, and the room itself, we call it the surroundings of the system. Okay, so what is the related is that we have to talked about the consumption power, okay? The consumption power is a problem, and the consumption power of the heating element. We need to reduce the consumption power. This is the first thing, okay? In the surroundings, there's also some related parameters. For example, the dissipation of energy is also affected in this. Okay, so number one, you have to, as you said, to get the effective parameters in the system and its surroundings. Okay. After that, you can see in the second point, literature review, what the researchers did. Maybe you collaborate with them, or at least you can take in consideration their works as a reference in your work. Okay. After that, and the third point, you can set your objectives. Actually, in this point, you can get, you can share your ideas with your team, for example, and you can get idea, for example. Let's see here. You know the consumption, okay, and at the same time, energy loss in the surroundings. How we can solve this problem? Okay, now this is the first thing you have to do. Actually, if we replace the heating element, if this heating element, for example, consume 3 kilowatt per hour, it's too much. Okay, and if you are electrical engineer, you can say I will replace this heating element. Okay, but still the problem. If we replace this, okay, and the dissipation energy not solved here, nothing will change to this guy. Okay, how we can solve this problem? Okay, the first thing, okay, it's good to reduce the power consumption of the heating element, but you need to change all the design, okay, to get another idea, innovative idea instead of this. For example, this is an example to solve this, okay? I know that what I talk about now, it's very, it's like an activity, it's not related to quantum or any of the previous talks, okay? That's why I talk now at the end of this. Now, this is the room, okay? If we change the technique of the heating in this to system, we need to circulate the air inside this place. And during that, we use very low power consumption heating element fixed on porous material with very high thermal conductivity, like copper or aluminum. The air, you can use a fan below here to push the air from down to this direction. So. So in this case, you can arise the temperature automatically, okay? Not in 1 hour, maybe in 30 minutes, not in 1 minute or 2 minutes, okay? Maybe in 30 minutes. But actually, you reduce the power consumption comparatively with the traditional system here. So you change all the system now, okay? So because you get the effective parameters on your problem, and then you see what the other researchers do. Now, it's good background to build your own design, your own idea. That's step 3. Okay. After that, you have you have to check the or instruments and operation. You can say operation methods or something like that. Suitable to some parameters in the feasibility study. Why? Because sometimes the other side, commercially, we have a cost of your product. This cost, you need to reduce all the expenses or during the manufacturing, including also the lab scale. Okay, so that's why you have to put in consideration some parameters from the feasibility study when you select your process of the preparation, okay, of the first prototype in the lab scale. Then in step 5, prepare resources and planning. You have to put a timeline, the schedule, and the sequence of your work with your team. Okay, but resources must be available cheaper. Also, because you at the same time you see some parameters in the feasibility study you can say that these parameters orient your work here at all. Okay. This and then the selected you will have here data tables, okay, and some graphs, for example, about what back to here about the consumption power with time, about the efficiency of the heating at all, of the heating system. So as we said before, we need to make thermal isolation here using material with very low thermal conductivity. I don't confuse between two things here. Very low thermal conductivity and in the room boundaries here to prevent the power energy dissipation. While in the new system here, we use very low power consumption heating element in metric with a porous material with high thermal conductivity. From your data and interpretations, you can get the optimized conditions for your problem to get the best solution. Okay. And then maybe in this case, for example, about the application, you can find another applications at the same time for the same idea. Okay. This is also every point here matching with searching commercially and maybe technicians from the other side, or maybe company or something like that, or factory uh, to discuss this. Okay, and then you will prepare questions. Uh, uh, this is what we call the marketing materials of the prototype, because the commercial side from as a researcher here, the specifications of your idea or your prototype, uh, everything, including also the dimensions and everything about this. Okay, why? Because in this case, stage, you need change everything commercially. Maybe you have to change the volume of your product. Okay, for example. Simply, yeah, you have to to go back at every step to the commercial or sorry, so to the technical team to share your with them. Um, the outcomes of lab scale or research work, at the end, you need to classify it, okay, according to the importance. Maybe you do something will be invention, okay, something new. You just do some investment, just a knowledge method, or you just optimize or enhance the efficiency of a system. Okay, this is really important because it's also commercially it's related to some legal bonds, like intellectual property, to protect your, uh, uh, for example, so also at the end, as you see here, software or hybrid. Okay. Uh, from perspective, service or project. Okay, let's see some examples. Actually, as we'll see later, talk about our team, ideas that we succeeded to produce it as a commercial products, and sometimes we have services. As you see here, data analysis and predictive maintenance services, or as we also talked before, something related to, for example, the or something like that. This is all. This is a surface, and this is also including the ERP, CAD, and all industrial software development. Okay, but in products, something physical, like machine or device or battery, as you see here, 20 examples. It's maybe concentrating action of things, and you correlate these things with each other to make something new. This is a project, okay? Not related to a new device or new service. Okay, here, this is a summary of the last slides here in this exact in this stage. When we start our prototyping system, okay, here we need to concentrate our meetings with the technical part to assure the final specification of our product or service, whatever what we do. This is we put here some industrial aspects like the mass production is different from the lab scale prototype. Okay, so you have to put in consideration here when the other side in the factory or in the company will produce this product in production. Okay, so you have to put everything here study. As we said before, because you need to reduce the expenses, okay, during the process, during the time, everything. And the team also maybe advise you to change something related to the shape, okay, or like it. Okay, in Egypt, I visited events like exhibitions or startups. I found actually new approach and very, very successful stories from the main idea to the final product. But I will talk here about our team, which is called National Team of Science and Technology, and what we do and what our plan in the next few months. Actually, we focus on these channels, okay, robotics, smart control, automation system, renewable energy and power systems, research, laboratories, tools, and instruments. Why? Because, you know, when you buy something fully computerized to do anything, this is very expensive generally, okay? Also, some internal devices and integrated solutions. Let's see some shots of this. For example, here, This is one of the projects that we succeeded in to build it in Marsa Alam. It's a solar station using monocrystalline solid cells there. And here we built a fully computerized articulated robotic arm to deal with hazardous materials. Okay, and actually this system prepare a nanomaterial in Jubra company for engineering industries. Also, we have lighting, as you see. Here, this machine, it's a packaging machine of the box in Shams University. We also succeeded to build our own mechanical system here. Completely, we make it, and we succeeded to operate this machine again. About research lab instruments. Actually, we focus on the characterization of the material thermally, magnetically, optically, and also about the combinational properties like thermoelectric. This is the old version. This is the old version of the thermoelectric measuring device. Okay, we have now a more sophisticated one. Also, we have another one for okay. My colleague here generated clean water from air using this device. Okay. This is our supporting partners. We also work with Egyptian companies. We have a plan to localize many industries related to the lab. Also in Swiss University, Dr. Muhammad Suki, I thank Dr. Muhammad Suki because he support us in his lab, and actually we have also many successful works there. Thank you for my friend. Thank you so much. I want to say something. This is at the end of the day, and maybe later, at any time you want, okay, we can present. I can prepare a full presentation for you in details, okay. Because the core of this hackathon is related to quantum mechanics, and it's not my discipline, by the way. That's why we can now talk to each other. Any questions? Anyone have a problem? We can discuss this. We can say how to produce a product. If you like to. Okay. Okay, that's good. You have to join. Actually, you have to. Every time I advise my colleagues and everyone in the study in the universities to make groups, okay, and to start connection with any related commercial organization. Okay, for example, I'm specialized in physics. Okay, now when I finished my study, I went to many factories and many organizations, and I just hear what they do, okay, at the beginning, and also there is you have many experts, okay, engineers and scientists in our universities. So just you have to join these groups to learn how to deal with this problem and to how to get the correct parameters. It's very important, okay, because all the next steps, okay, it's depend on this. That's why I call this point a key point. Key point, okay, to find seriously, it's very important. We can make sessions for this to train, okay, and many disciplines. It's for example in electronics, in chemistry, for example, in mechanics, okay. We have a lot of ideas. We can share this, and you can train about how to think from scratch to get the logical sequential steps to precisely identify the problem, and then you can succeed in the other points. Thank you so much.
لو في أي حد عنده سؤال.
Yeah, I would like to thank everyone for their contribution today and yesterday, and for the benefit of time we have been overrunning. I would like to invite everyone, judges and speakers who are still in this room, to kindly maybe follow me to the place of where we'll have a discussion. Thank you.